Hello, everyone. Thank you for attending my talk. My name is Ankush Das, and today I'll be presenting our work on resource-aware session types for digital contracts. This is joint work with my collaborators at CMU. And let me begin with an overview of my talk. So today I'll be talking about the Nomos programming language that we have designed for the domain of digital contracts. In this domain, the challenges that developers often face are threefold. First, contract protocols are often violated. Assets are accidentally duplicated or deleted. And finally, it's difficult to automatically infer the execution cost of programs. In response to these challenges, we have designed the theory of resource aware session types, which is also the driver behind the Nomos language. In particular, it addresses these challenges as follows. Session types express and enforce contract protocols. Second, linear types track assets, preventing their duplication or deletion. And finally, resource-aware types automatically infer the execution cost. So now let me begin with the first part of the talk explaining digital contracts and the challenges developers face in this domain. So digital contracts are essentially programs that implement some complex transaction, often between distrusting parties. Some examples of this include, for instance, online transactions like on Amazon or eBay, wealth management applications like Wealthfront or Robinhood, and most recently, this has become popular in the form of blockchains and cryptocurrencies like Bitcoin or Ethereum. To understand the challenges developers face, let me take a simple example. Suppose I am running an auction, auctioning off the Mona Lisa painting. And let's say there are three bidders in my auction, bidders 1, 2, and 3 with their respective bids. Now, what would the protocol of such an auction contract look like? Well, first, each bidder will submit their bid to the auction, and then at some point, the status of the auction, which is currently running, will transition to ended, indicating that the auction is no longer accepting new bids. And then the contract would determine the winner of the auction. So suppose here bid 3 is the highest bid, bidder 3 is the winner of the auction. The contract will then transfer the Mona Lisa painting to bidder 3, and bids 1 and 2 will be returned back to the bidders. Now suppose you wanted to implement this auction deployed on a blockchain, you would do it in this language called Solidity, one of the most popular smart contract languages out there. And the auction will be handled in these two functions. The first will be the bid function, where you compute the value of the bid, the address of the bidder, you store it in a local dictionary called pending returns, and you check if the bid is greater than the highest bid, you update the highest bidder and the highest bid. The second phase is handled by the collect function, where you have a require clause that the sender cannot be the highest bidder, because the highest bidder does not get their bid back, they get the Mona Lisa painting instead. And then you look up in the dictionary to compute the amount that must be sent to the bidder, and then you send it, and then you return. So if we turn our attention to this collect function for just a second, I'm claiming that there are actually several bugs in this code. And let's take the first example. What happens if collect is called when the auction is still running, right? Clearly nothing in the code prevents this from happening. So it's up to the programmer to add a clause that requires that status must be ended at this point. But the language has no way of recognizing this protocol violation. Second, what happens if collect is called twice by the same user? They will get their bid back twice, even if they have bid only once. So it's up to the programmer to update the dictionary and set pending returns for the sender to 0. But again, the language has no way of recognizing this problem. And finally, let's say even if the program is correct, and if the user wants to issue this transaction, they will have to pay a fee to cover the execution cost. How much fee should they pay? Again, the language has no support for automatic execution cost prediction, so that the user is aware of the fee that they should submit along with this transaction. So these three challenges are typically what developers face when they are programming smart contracts. Now let's see how the Nomos language addresses these challenges. And to do that, I need to introduce resource-aware session types. But let me begin by first introducing session types, which are essentially a system for implementing message passing processes. So the first step here is to think of the bidder and the auction as two different processes which are connected by a channel. And then I'm going to assign a session type to this channel. And that brings me to the first key idea behind the Nomos language, which is that we use session types to express and enforce contract protocols. How is that expressed as a session type? Well, let's look at the auction session type. So here I have the type at the bottom. Don't get scared. I'll explain this step by step. So the auction starts in the running phase. So here the session type enforces that the contract must first send the running message to the auction, indicating that the auction is running. And then the bidder can only reply with a bid message. They cannot send any other message. After the bid, the bidder sends their money corresponding to their bid. And then the type recurses back to the auction so that other bidders can place their bids into this auction. In the second phase, when the auction has ended, the session type enforces that the auction sends an ended message to the bidder, and then the bidder can only reply with a collect message. Once they send the collect message, now the auction has a choice either to send the one message if the bidder has won the auction, followed by sending the Mona Lisa painting, or if the bidder loses the auction, then the auction sends the lost message followed by their bid back. And then in either case, the type recurses back to the auction so that more bidders can collect from the auction. And so as you can see from the type, bids can only happen when the auction is running, and collects only happen when the auction is ended. So this protocol of communication is exactly captured in the session type and statically enforced. Now, what about asset preservation? Well, that brings me to the second key idea behind the Nomos language, which is that session types in Nomos are carefully designed such that they are in a Curry-Howard isomorphism with linear logic, which you can really think of as the logic of assets. So the session type that I showed you earlier can automatically enforce that objects of type money or Mona Lisa can neither be duplicated nor discarded. They can only be transferred between processes. So with no additional machinery, just by using session types, you get asset preservation for free. You don't need to do anything extra to the language. But what about resource analysis? How do we infer the execution cost? So let's assume that the cost of bidding into the auction is 2 units and the cost of collecting out of the auction is 3. Now that brings me to the third key idea behind the Nomos language, which is that Nomos enhances session types with this notion of potential, which you can also think of as fee, that pays for the execution cost. And this is what we call resource aware session type. So here now you will see the type has these left and right triangles. What do they mean? Well, the left triangle 3 means that the user pays 3 units as fees at the start of the execution. And the right triangle return whatever leftover fee back to the user in the end. So in the bid branch, the user pays 3 units, 2 units get consumed for bidding, and 1 unit is returned back. In the ended branch, the user pays 3 units, all 3 get used up to pay for collecting, and the user doesn't get back anything in the end. On top of these potential annotations, the numbers 3, 1, 0, and 0, they are automatically inferred using the LP solver, which is built into the language. So the burden of computing these numbers, these annotations, is not on the programmer. The language can take care of that. All right, so that brings me to the end of the talk. Let me just conclude by saying today we looked at the Nomos language and the domain-specific challenges that it addresses for digital contracts. Thank you.